you're trying to solve AX equals B, A equals A transpose, and singular. Okay. Now the thing is, because this matrix is singular, this system does not necessarily have a solution. So this has a solution if and only if B is an element of a range of A. So this is something that's true in general for any system of linear equations, no matter what kind of matrix you have. Now, the other thing is, in general, the range of A is the orthogonal complement of a range of A is the null space of A transpose. But in this case, A is a symmetric matrix. So it's the so what you have is your vector space is partitioned to a range of A and a null space of A. Now, your vector B that you're given could equal anything. So it may have a component in the null space of A. So B tilde. So what you will instead need to do, in order for your iterative method to have a chance of converging, is you solve AX equals B tilde, where B tilde is in the range of A. But the thing is, you don't want to just pick any vector in a range of A. It should be a reasonable approximation of the original B. So in fact, it should equal the orthogonal projection of your original B on the range of A. And in other words, what you need to do is you have to orthogonalize your original B against the null space of A. Now the thing is, how can you do that in an efficient manner? Because computing the null space of a general matrix is usually a very expensive operation. But this is where, but the thing is, this is where part A of a problem comes into play. Because in part A, it's supposed to show that the matrix M inverse N has at least one eigenvalue equal to 1. So part A gives you a way of figuring out what is in your null space using your iterative method. So the idea is B has a unique decomposition into B tilde plus another vector I'll call Bn. B tilde is in the range of A, and Bn belongs to the null space of A. Okay. So the idea is, if you can figure out what portion of B is in the null space of A, then you can orthogonalize against it and get rid of it. And then you have a system that you can solve. Okay. Now, so the challenge is, how do you find this when you don't know the null space of A? And the key to this question is to use your iterative method. And this is not going to make any sense unless you've done part A. So part A kind of lays the groundwork for this, because it relates the null space to your iterative method. So I'm going to stop there and see what you guys can do with that. Have you worked out part A?
I think so.
Okay.
I'm not quite sure, but
Okay, because the thing, I'll make a comment about the convergence of iterative methods in general, and that is, you can think of your error as being expressed as a combination of all the eigenvectors of A. Not A. All the eigenvectors of M inverse N. And as you carry out iterations, the components of your error corresponding to eigenvalues less than 1 in absolute value, those are going to go to 0. And normally you want that to happen for all components, and your iterative method will converge. If you try your iteration on the original problem, the iteration will not converge, because M inverse N is going to have at least an eigenvalue equal 1. So you have to think, well, what is the consequence of that? Because when an iterative method converges, the difference between your iterates is supposed to be going to 0. But in this case, it's not going to happen. So if you keep iterating and you find the difference between iterations is not going to 0, what is it converging to? And what do you know about the vector that you obtain from that? Because when an iterative method fails to converge because it has an eigenvalue equal 1, what's left corresponds to eigenvectors corresponding to eigenvalues that are greater than or equal to 1 in absolute value. So basically, you're using the failure of your iterative method to figure out how to fix it. Actually, I'll go ahead and write this down. Actually, I don't normally do improvisational things mathematically because it usually goes bad, but I'm going to try it anyway, in case it might make the problem easier. Okay, because when you have a convergent iteration, you have a difference between iterates, xk plus 1 minus xk, should be converging to 0. But let's take a look at this difference, xk plus 1 minus xk, for a general iterative method. Well, xk plus 1 is equal to m inverse nxk plus b. So let's take a look at xk plus 1 minus xk. Let's look at that difference. So I'm going to distribute here. So m inverse nxk plus m inverse b minus xk. Just subtracting xk from both sides. So that is equal to m inverse n minus identity times xk plus m inverse b. Okay. Now, I can try manipulating this because I'm going to replace identity here with m inverse m. So what you get is M inverse n minus m xk plus m inverse b. But n minus m, what is that?
N minus n.
Yeah.
Negative A.
Yeah, it's negative a. So this is m inverse, and actually I have m inverse multiplying everything. So this is b minus a xk. Well, what does that represent?
The residual.
Yeah, it's actually a residual. Okay. Unfortunately, this is not going where I wanted it to. But it was worth a shot. Okay, so if I back up just a little bit, okay. So if I focus back on this step right here, now, okay, because, oh, okay, B I can write as, I still have the m inverse. B I can write as ax. X is your exact solution. But a is equal to m minus n. So that is equal to x minus m inverse n x. So in fact, actually, okay, this is better. I'm going to work with that instead. Okay. So now what I have is m inverse n xk. All right, and then I have m inverse b, which is okay, minus x plus x minus xk. All right. Okay. So in fact, I can write this as m inverse n. Okay. This is the same as identity minus m inverse n. Times ek, where I define ek as the error after k iterations. Okay. So this we have a relationship between consecutive iterates and the error after k iterations. However, this error is known to be m inverse n to the kth power times the initial error. It keeps getting multiplied by m inverse n from one iteration to the next. And the thing is, this error is supposed to be going to 0. But if the initial error has any component in a direction of eigenvectors corresponding to eigenvalues of 1, this will not go to 0. So this, the way it is now, is not going to 0. For a general B. Now the thing is, my initial error has a component in the range of A and a component in the null space. M inverse n applied to the component in the range is going to go to 0. Because